Okay, folks, so now we are moving on to the next section, which is section 8.4. This is day 1 of section 8.4. And we're talking about solving trig equations. So this is typically the section that causes people a lot of problems in this chapter. The identities are an issue, but that's really just a matter of memorizing. There's really nothing to the identities other than memorizing and then just practicing the couple of problems that go with each identity, which we've seen over the last few days. What we're going to do now is we're going to talk about solving trig equations. You need to make sure that you understand the issues that we're going to discuss over the next couple of videos. We're going to spend 3 days on this section. You need to make sure that if something doesn't make sense, you back up, you rewind, and you watch it again and make sure that it sinks in. And if not, then you need to ask me about it in class so that we can get you up to speed. This tends to be somewhat mechanical stuff, but if you don't understand the mechanics of what you're doing, you're going to be completely lost on it. I also want to stress before we even get started that one of the keys to doing these problems correctly is you've got to read the directions. The number one mistake that people make and lose points on the quiz and test in this chapter, specifically from this section, is they don't read the directions. I ask for degrees, they give me radians. I ask for radians, they give me degrees. I ask for all values, they give me just between 0 and 360. I ask for just between 0 and 360, they give me all values. Okay, they always seem to be doing the opposite of what I'm actually asking for because they're guessing at what I'm asking instead of actually reading what I'm asking them for. So please make sure that you read the directions. All right, let's take a look at what we're going to start with. The first example is real simple and basic, but it just kind of reiterates what it is that we're doing. They want to know, is pi over 4 a solution of the equation sine of x plus cosine of x equals 1. And just like problems you've been doing since algebra or even pre-algebra, if you want to know if a value is a solution of an equation, you plug it in for your variable. So the question is sine of pi over 4 plus cosine of pi over 4 really equal to 1? Well, these are unit circle values. Pi over 4, we know, is square root of 2 over 2, comma, square root of 2 over 2. This is the section where you really, really need to know your unit circle. Okay, this is what we've been building up to all this time with our unit circle quizzes. So sine is the y-coordinate, that's square root of 2 over 2. Cosine is the x-coordinate, that's also square root of 2 over 2, equals with a question mark 1. This is 2 square root of 2 over 2's. Those cancel out, and we get square root of 2 equals 1, which is clearly not true. Therefore, use my little 3 dots for therefore no, pi over 4 is not a solution. Very, very basic. I think the first couple of problems on the homework section. Sorry about that. The microphone fell off here. The first couple of problems in the homework section, although I probably will just assign maybe one of them to you, if that. But the first couple of problems just ask you to do this kind of thing. The reason I brought it up, since I probably won't assign them to you, they're pretty basic. I want to just talk about the difference between a trig equation and a trig identity. This, apologize for that. Let's try getting the proper shape here. This is a trig equation. We know that because we just plugged in an angle and it was not true. A trig identity is a trig equation that is true for any angle x or theta or whatever variable we're using in the identity. As long as we use a valid angle, it will always work. This is a trig equation. Clearly, this does not work for all values of x. And that's what we're going to be working with a lot in this particular section Although we will use some of our identities for doing some substitution, we're really not solving identities. We're solving equations. We're finding the actual values that really do make this thing true, since most values do not. All right, so that's example 1. Very, very basic. Now, example number 2 that I want to talk about, and we're going to focus on unit circle solutions today, and tomorrow we'll start to talk about what happens when they don't give you unit circle values in the problem. So number 2 is going to tell us, I'm going to switch to black here because I prefer that for my ink color. Number 2 is going to say solve sine of x is equal to 1/2 for x between 0 and 2 pi. Now, another way that they can write this, just so you know what they're talking about, is they could say solve for x in the interval round bracket 0 to 2 pi round bracket. Do you guys see, hopefully, that this is exactly the same thing as this? It's the open interval because there are no equal to's here. So that means that we have to be strictly between 0 and 2 pi. All right, so let's take a look at how we do this. Well, in order to do this, we have to get x by itself. Now, here's where a button on your calculator that we've kind of alluded to, but we haven't really used in this class yet, comes into play, and that is the inverse sine function. So written above sine on your calculator, not that we're going to use the calculator for this exact problem, but starting tomorrow we will. Written above sine on your calculator is inverse sine. Let me pull my calculator up here real quick. Notice that written above sine, if you can see it on the video here, is inverse sine. So if I hit second function and then sine, I get sine and it looks like the -1 power. It's not really a -1 power. It does not mean 1 over sine. It's not cosecant. We've talked about that before. This is function notation. So this is the inverse function, like f inverse of x. And what this does is the following. What this means is that when we have x equals inverse sine of 1/2, that's how we get x by itself, first of all. Remember back from inverse functions, so if I take this and I take the inverse sine of both sides, when I take a function and its inverse and composite them in either order, either sine of inverse sine or inverse sine of sine, they essentially cancel out and just pop out whatever you're plugging into the function. And so this just gives us x equals inverse sine of 1/2. So that's where this came from. So you're taking the inverse sine of both sides. That's how you get rid of sine. Remember, this is not sine times x. Sine is not a number by itself. Just like a square root is not a number by itself. You have to put something in it. Same thing with sine. You have to put an angle in it. So we can't divide by it, but we can take the inverse to get x by itself. Now let me talk about what this means real quick. What this means is that we want to know what value of x makes sine equal to 1/2. And x is going to be an angle. So what value of x, what angle makes sine of x equal 1/2? That's what this really means when you see x equals inverse sine of 1/2. Here's the thing that you need to understand. Remember that what sine does is it takes an angle and it gives you back a ratio, opposite over hypotenuse. That's the 1/2. What inverse sine does, remember from inverse functions that we swap x and y. Our inputs become our outputs and vice versa. And so what the inverse function does is it takes in the opposite over hypotenuse ratio and it returns a value for the angle that creates that ratio. So the output of a sine function is a ratio. The output of an inverse sine function is an angle. That's very important to understand. We're trying to solve for our angle x. That's why we're using inverse sine here. So we have to ask ourselves, what value of x, what angle makes sine equal to a half? We're going between 0 and 2 pi. 1/2 is a unit circle value, so we're going to think about where is sine equal to 1/2. Well, between 0 and 2 pi, there are two places where sine is equal to a half. Over here at pi over 6, and then over here at 5 pi over 6. Those are the two places where sine is equal to 1/2, because this is rad 3 over 2, comma 1/2, and this is negative rad 3 over 2, comma 1/2. So there's our sine equals 1/2. And so our answer then is going to be x is equal to pi over 6 and 5 pi over 6, and you're just going to list the answers out. That's the solution to this problem. So if we want to solve sine of x equals a half, this is what we get. Pi over 6, 5 pi over 6. Now, there are a couple different ways that they can ask this, and this is why I said that you have to make sure you pay careful attention to the instructions. One of the things they could say is, instead of asking you to solve for x between 0 and 2 pi, one of the things they could do is they could ask you to solve for x between 0 degrees and 360 degrees. Or they could write it as an interval. Okay, so the interval here would be round 0 degrees to 360 degrees round if it was given to you that way. Two different ways of writing the same thing. Well, notice it's not going to change where sine is equal to a half. The only thing it's going to do is change how we write the solutions. So now instead of pi over 6, this will be 30 degrees. Instead of 5 pi over 6, this will be 150 degrees. And so that's the only thing that would change, is the way, the units that you write your answers in. So this would be the solution now. Now, there's another thing that they could do. And that is, they could ask us to do it in radians again. But instead of asking us to go from 0 to 2 pi, they could say for all values in radians. Well, this part of the work doesn't change. Let me go back to my pi over 6 and 5 pi over 6. But here's the thing. We get our pi over 6. We get our 5 pi over 6. But what do they mean by all values? They mean all values, meaning any angle in the entire universe that makes sine equal to a half. Well, are there any other angles that make sine equal to a half? And the answer is yes, there's an infinite number of them. Because remember, instead of pi over 6 and 5 pi over 6, couldn't I go all the way around the circle and then an additional pi over 6? And won't that, since it gives me the same terminal side, give me the same values, and therefore sine will be 1/2 again? And the answer is of course. So it turns out that we can add 2 pi. If I can add 2 pi, then I could also keep going around another time and add a total of 4 pi to it. So go around the circle twice and then to pi over 6. Same thing with 5 pi over 6. Around the circle once plus another 5 pi over 6. Around the circle twice plus another 5 pi over 6. We could also go backwards. I could also go backwards a full 2 pi and then turn around and go forward pi over 6. And so the idea is, and we've seen this before with coterminal angles, that any angle that's coterminal with one of these solutions is also going to be a solution. So the question is, how do we write these infinite solutions? And the way that you write these infinite solutions is very easy, because there's a convention for it. And the convention says that what you do is you write plus 2 pi k on each of your original solutions. That means that we're going to add 2 pi times some constant k, or some variable k, I should say, where k is an element of the integers. That's what the double z stands for. Remember from the beginning of the year when we talked about those symbols. The z is the integers. Positive and negative whole numbers and 0. When k is 0, then we get pi over 6 and 5 pi over 6. When k is 1, then we get pi over 6 plus 2 pi, which is 13 pi over 6. And we get 5 pi over 6 plus 2 pi, which is 12 pi over 6 plus 5 pi over 6, 17 pi over 6. So that would be what we get the second time around the circle. and the third time, and the fourth time, depending on what we make k. If k is -1, then we go backwards once around the circle. And so since it's understood by anybody reading this that k is going to be an element of the integers, you don't have to write this part over here. It's understood. This is a commonly or universally accepted format for writing these answers. And so this would be how you write your solutions when they ask for all values in radians. Do not give me the answer in degrees if they ask you for radians. Do not give me the answer in radians if I ask you for degrees. Okay? And that's part of reading the instructions. Do they want all values or just one time around the circle? And what kind of units do they want from us? If they give us the interval like they did a little while ago, where we started out where it said on the interval 0 to 2 pi, that is telling us two things. Number one, it's telling us they only want us to go around the circle once, 0 to 2 pi. It's also telling us that they want our answer in radians, not degrees. And if you give me the answer in the wrong units, I will dock you a couple of points on the test because you're not reading the directions. You're not following the instructions. Okay, let's run through a couple of other examples. I know the video is already running a little bit long, but I need to give you a couple more examples just so you get the feel for what's going on. The first of those examples, oh, and clearly on that last one, they could also ask us to find all values in degrees as well. We would just, instead of adding 2 pi k, we would do something like 30 degrees plus 360 degrees k, and 150 degrees plus 360 degrees k. These would be the degree version in case this said in degrees instead. All values in degrees. Helps if I spell degrees correctly. There we go. So then your answer would look like these two. Okay, let's move on to the next example. This time we have cosine squared theta plus cosine theta minus 2 is equal to 0, and we want to solve for all theta in radians. The key here is all theta, all angles, and in radians. So we're going to need our plus 2 pi k. What you do here goes back to when we first started working with algebra and trig, and that is we've got to factor this thing. So this factors into cosine of theta plus 2 times cosine of theta minus 1. Always FOIL it out to check it. This is just like x squared plus x minus 2 would be x plus 2x minus 1. Same thing, but instead of x, we're using cosine of theta. So now when I set this equal to 0, we're going to get cosine of theta plus 2 equals 0, which gives us cosine of theta equals negative 2. This one is going to give us cosine of theta is equal to 1. Now to get theta by itself, we're going to take the inverse cosine of negative 2. And we're going to take the inverse cosine of 1. In other words, where is cosine equal to negative 2, and where? What angle is cosine equal to 1 at? The first part, cosine equals negative 2, so theta equals inverse cosine of negative 2, asks us what angle makes our cosine value negative 2. And the answer is there isn't any. Because we know the biggest cosine can be is 1, and the smallest it can be is negative 1. So there are no angles that make cosine equal to negative 2. Therefore, we get no solution from that first piece of our equation. That's fine. Now we move on to the second piece. Where is cosine going to be equal to 1 in radians? And the answer is going to be right here at 0 radians, and then it doesn't happen again until we get to 2 pi radians, and then 4 pi, etc. So our answer the first time around the circle is 0 radians, so we get theta equals 0 radians, but because they want all solutions, we have to put the plus 2 pi k on it. And obviously 0 plus 2 pi k really just simplifies down in this case to 2 pi k. So when k is 0, theta is 0. When k is 1, theta is 2 pi. When k is 2, theta is 4 pi. When k is negative 1, theta is negative 2 pi. All of those will give us a cosine value of positive 1. And so here is your final solution set. It's an infinite number of answers, but all written in one expression. Okay, I want to take a look at one more example on this video, and then you guys can get started. The last example for today is tangent squared x is equal to 3. And we want to solve this for x in the interval 0 degrees to 360 degrees. So we're going one time around the circle, and we're in degrees. That's what that tells us for our answer. So what we do here is we have to get tangent of x by itself before we can get x by itself. And so we're going to square root both sides. When we do that, you need to make sure you put in plus or minus because we square rooted both sides. Do not forget that. So we get two different values for tangent of x. Tangent of x equals square root of 3. Tangent of x equals negative square root of 3, which means x is going to be equal to inverse tangent of either positive or negative square root of 3. I'm going to write it as two separate parts because we're going to find them individually. So the first thing is, where is tangent rad 3, and is this a unit circle value? And the answer is yes. When you see something like a rad 3 or you see something like a rad 2, those radicals come from our unit circle values. So the question is, where is tangent going to be square root of 3? Well, where square root of 3 pops up is one of two places. Either square root of 3 over 2 comma 1/2 or 1/2 comma square root of 3 over 2. I'm ignoring the whole plus or minus issue right now. We'll touch on that in a minute. I'm just talking about the numerical value. Remember that tangent is sine over cosine, y over x. So the question is, does this simplify to square root of 3, or does this one, y over x, simplify down to square root of 3? And the answer is it's this one, because when we multiply by 2 over 1, instead of dividing by half, the 2's cancel and you just get rad 3. So this is the situation that we're looking for. Okay? That's the one we want, not this one in this case. Now, if it was 1 over square root of 3 here, or square root of 3 over 3 if it was rationalized, then it would be this one that we want and not this one. So the question is, where is tangent going to have, what angle has an x coordinate of 1/2 and a y coordinate of rad 3 over 2? And the answer is, up here at 60 degrees, we have those values. Now, there's nowhere else on the circle where x is 1/2 and y is rad 3 over 2. But there's another quadrant where tangent is positive, and that is down here in quadrant 3, which would be 240 degrees. Why? Because x is negative 1/2, y is negative square root of 3 over 2, and negative divided by negative gets us back to positive square root of 3. So it turns out that we get two different values, and that's typically the case. You're going to get two answers for each part of these things if you're going one time around the circle. So from this first piece, we get x is equal to 60 degrees and 240 degrees. Now, when we look at negative rad 3, tangent is negative up here and down here at 120 degrees and at 300 degrees. Those are the two places where tangent is going to be negative square root of 3. Tangent is negative in quadrants 2 and 4 because that's where x and y have opposite signs, SIGN signs. Right? In quadrant 2, x is positive, x is negative, y is positive. In quadrant 4, x is positive, y is negative. So y over x, tangent is going to be negative. And so we end up with 4 solutions altogether as our final answer. And there we go. Now, if they said all values in degrees, then instead of writing it like this, you would write each one out, and next to it, you'd put a plus 360 degrees K. And we'll talk more about that in a future lesson. All right, so that's going to conclude the lesson for today. You're basically just doing these with unit circle values. Make sure that you go back and re-watch anything that didn't totally sink in. It's very important that you guys go back and watch anything that's not totally sinking in. And please try at least a couple of the problems on your own while this video is fresh in your mind, and then you can continue working on it tomorrow in class.